Black holes. You've heard of them, but there's so much more than just giant vacuum cleaners in space. They are, without a doubt, the universe's ultimate monsters. These are regions of space where gravity is so intense, so absolute, that it literally breaks the fabric of reality. We're not just talking about objects here, we're talking about places where our understanding of physics, space, and even time itself just comes to a terrifying end. So, let's begin our descent. For the longest time, black holes were just a bizarre prediction, a ghost in Einstein's equations. But then, in 2019, humanity stared right into the abyss, and it stared back. This is M87, the very first direct image we've ever taken of a black hole's shadow. It was a monumental achievement, let me tell you. The Event Horizon Telescope project basically turned the entire Earth into one gigantic observatory just to capture this. That glowing ring you see? That's superheated gas swirling around the edge at incredible speeds. And right in the center, well, that's perfect absolute blackness. That's the point of no return. And this quote from physicist Paul Chesler really gets to the heart of what we're talking about today. See, we're not just exploring a weird object in space, we are proving the absolute limits of what we know. A black hole is like a cosmic error message, a place where our most powerful theory of gravity, general relativity, simply stops working. It just breaks. All right, so let's start our descent at the most famous and maybe the most feared part of a black hole, that boundary you can only cross one way. So, if we're talking about a basic, non-rotating black hole, the structure is actually pretty simple. It's really defined by two key parts. You've got the singularity right at the center. That's the point of supposedly infinite density. And then surrounding it, you have this invisible boundary, the event horizon. These are the two landmarks on our, well, let's call it a terrifying journey. Now, the event horizon isn't some physical surface you could bump into. In fact, you wouldn't even feel yourself crossing it. It's more like a geometric line drawn in space-time. It's a one-way door. Before you cross, you can still get away. But the moment you're past it, every single possible path you could take, forward, back, left, right, every path leads deeper into the black hole. Escape becomes not just hard, but conceptually impossible. And research has confirmed this isn't some kind of super dense planet or star. It's a true void. When a star or, anything else falls in, it gets swallowed whole. It just disappears entirely from our observable universe, almost like it never existed in the first place. It's the ultimate cosmic vanishing act. Okay, so a one-way ticket to oblivion is weird enough, right? Well, the real mind-bending stuff starts when we look at what black holes do to time itself. This is one of the craziest paradoxes in all of physics. Imagine you're watching your friend fall into a black hole from a safe distance. To you, it would look like they're slowing down as they get closer to the event horizon. Slower and slower, until they seem to freeze right at the edge, their image stretching out and fading to nothing over an infinite amount of time. But what about your friend? From their perspective, their watch is ticking normally. They feel no change in time as they sail right past that point of no return. So in a way, they are both frozen in time for eternity and plunging to their doom all at the exact same moment. How wild is that? And as the legendary physicist Kip Thorne puts it, this isn't a small effect. To us, looking from the outside, time at the very edge of a black hole nearly grinds to a complete stop. This isn't science fiction, folks. It's called gravitational time dilation, and it's a proven real-world consequence of Einstein's relativity. Okay, so we've crossed the point of no return. We are now inside the event horizon. What happens next is completely inescapable and, frankly, utterly horrifying. Once you're inside the horizon, the fundamental roles of reality are rewritten. Space and time literally swap their roles. Think about that for a second. Right now, you can move anywhere you want in space, but you're forced to move forward in time, right? Well, inside a black hole, you're now forced to move toward the singularity just as relentlessly as you're forced to move into the future. It's no longer a place you can avoid. It's a direction in time. All roads lead to the center. And the end? It's not pretty. The tidal forces would shred you atom by atom, crushing you down into your basic building blocks, quarks, long before you ever got close to the center. And for the kind of black holes that actually exist in our universe, the rotating ones, the journey has stages. First, you cross that outer event horizon we talked about. But then, you approach a second, really unstable boundary called the inner horizon. You can think of it as the final, violent doorway where space-time itself starts to warp and unravel exponentially right before you hit the end of the line. So we finally arrived at the end of the journey, the singularity. But what is it really? Well, here, physicists are forced to choose between two deeply unsettling possibilities for how it all ends. So you have two flavors of doom. With a space-like singularity, your destruction is a moment in time. It's inevitable, just like tomorrow is inevitable. But for a time-like singularity, it's a place in space you might be able to avoid. Now that sounds better, right? Well, here's the catch. A time-like singularity is chaotic, unpredictable. Light can escape from it, which means it could influence the outside universe in ways physics simply cannot predict. It breaks our understanding of cause and effect everywhere around it. So, in a moment of some pretty dark scientific understatement, physicists call the space-like version, the one where you're guaranteed to be obliterated, preferable. And why? Because at least with that one, physics only breaks down at that single, unavoidable point. With the other one, all of physics breaks down everywhere. The good news, if you want to call it that, is that recent research suggests real black holes probably have the preferable, inevitable, space-like kind. Cold comfort, right? So your body may be crushed into quarks, but what happens to the information that made you, well, you? Your memories, your experiences, your unique arrangement of atoms. This question leads to one of the deepest and most profound paradoxes in all of modern physics. So here's the thing. Stephen Hawking figured out that black holes aren't entirely black. They slowly leak radiation and eventually evaporate over unimaginable timescales. But if the black hole eventually disappears and nothing can ever escape it, what happens to the information about everything that fell inside? Is it just deleted from the universe? And this, right here, is the paradox. It's a head-on collision between our two best theories of the universe. Einstein's general relativity says yes, that information is gone forever, locked away behind the event horizon. But the laws of quantum mechanics are just as rigid. Information can be scrambled, but it can never be truly destroyed. One of these bedrock theories of physics, as we currently understand them, has to be wrong. Now, you might be thinking, well, isn't this like burning a piece of paper? The information seems lost, but it's really just encoded in the smoke and ash. But here's the problem. That's not what Hawking found. The radiation coming from a black hole isn't made from the stuff that fell in. It's created from quantum fluctuations in the vacuum of empty space right near the horizon. And that means the radiation is totally generic. It contains zero information about what's inside the hole. Hawking's argument is actually so powerful that it's basically a theorem. It says that if you assume our standard physics works, and you assume the horizon is a smooth, featureless place, an information-free zone, then information has to be lost. It's an unavoidable conclusion. So to solve the paradox, one of those core assumptions has to be wrong. So what gives? Well, as physicist Samir Mathur points out, the answer probably lies in a deep lesson from quantum gravity. And that lesson is this. Our simple picture of a single, smooth black hole is probably just wrong. In reality, quantum mechanics allows for a mind-boggling number of possible, complex states for a black hole to be in. And maybe that's where the information is hiding. And this leads us to a pretty radical final thought. What if the solution to this whole puzzle is to just get rid of the inside of the black hole altogether? A wild idea from string theory called the fuzzball model suggests that a black hole isn't an empty void with a singularity at all. Instead, it's a tangled, messy, horizon-sized ball of fundamental strings. In this picture, there is no event horizon. There is no singularity. The information never crosses a point of no return. It just gets imprinted on this fuzzy surface. So could the darkest truth about black holes be that they aren't empty pits after all, but are instead these unimaginably complex quantum objects, hiding all their secrets in plain sight?